Greetings everybody. So today we are going to discuss about a new topic which is based on acids, bases and salts, such that we are going to first discuss about the one shot here. We are having the physical characteristics of acids and bases. Now there are two categories in which we classify acids and bases. First is the physical characteristics of acids and bases. Second is the chemical characteristics. Rest of the portion is about chemical characteristics. So first let us discuss what are the physical ones. Acids basically are sour in test are those chemicals, those solutions which are sour in test, right? Those which are sour in test because of their H ions present. Now we are going to discuss why. And basically they have a characteristic that they can corrode metals. This is also a characteristics of the acid, as well as they have positively charged hydrogen ions. This is a physical characteristic. And they turn blue litmus red. They turn blue litmus red. As well as when it comes to bases, and on the other side acids are corrosive such that they can burn if they are put on a particular object. When it comes to bases turn red litmus blue, such that these turn red litmus blue. They taste bitter in taste. Example of acids is very common, such as melanoic acid, one which is found in apples and pears, and formic acid, as well as which is found in grapes, as well as there is citric acid found in lemon, ascorbic acid, orange, lemon. So these are certain types of acids. When it comes to bases turn red litmus blue, and they have test which is bitter. They have negatively charged hydrogen ions, and these are slippery. Whenever we touch bases, these are kind of slippery. And most hand soaps and drain cleaners, all of these are bases. These are application. Strong bases are caustic, which means strong bases are caustic, such as sodium hydroxide, caustic soda. Sodium hydroxide, caustic soda, it is caustic, right? So these are some characteristics. When it comes to the first topic which we are going to study today is about the Arrhenius theory. Now acids and bases uh, during the earliest time were difficult to classify. So the first theory which was presented in regard to classify the chemicals or solutions as acids, or chemicals and solutions as bases, was given by Mr. Arrhenius. And Arrhenius here, what did he say was that those substances, those chemicals which possess hydrogen ions, those substances which dissolve hydrogen ions when dissolved in water, are known as acids, and those substances which produce OH ions when dissolved in water are known as bases. And these at that time were known as Arrhenius acids and Arrhenius bases respectively. Such that Arrhenius acid basically uh, is the one which is having hydrogen ions itself, and when it is dissolved in water it produces H ions or protons, or we can also call them as protons, because here these are, you know uh, if we can call hydrogen ions as proton in such a manner that here hydrogen is having only one electron in its outermost shell. When it loses its one electron, it becomes hydrogen proton, and that hydrogen proton will be known as the characteristic or symbolism for acid. It is a symbol for an acid, such that any acid which is having that hydrogen ion and producing that hydrogen proton in the water, it will be known as an Arrhenius acid. Likewise, when it comes to Arrhenius base, if Arrhenius base can be considered as any substance which causes to produce OH ions when dissolved in water. Now, you might be hearing the word water again and again. So, the application is only limited to those substances which are able to dissolve in water, which means Arrhenius theory is only applicable in aqueous solutions. Those substances which are in aqueous forms, or those are in the form, or those are dissolvable in water, can you know fulfill the Arrhenius theory. Now coming to another point, there are some examples over here. uh, Sodium hydroxide, sodium OH, NaOH. Now when it is dissolved in water, it basically dissociates into sodium ion, OH ion in the aqueous solution, such that the sodium and OH ions indicate that here there is presence of a basic solution over here. There is presence of basicity, such that OH ions represent the basicity of the solution. While on the other side, potassium hydroxide, likewise, when it is dissolved in water, it produces potassium ions, hydroxide ions, and their hydroxide ions basically represent the basicity or the basicness, alkalinity, right? When it comes to likewise, if we talk about um let's say HCl, HCl when it is dissolved in water, it basically is having hydrogen atom, and when it is dissolved in water, what actually happens is that it dissociates into hydrogen H positive plus chloride, such that this H positive hydrogen here, H positive hydrogen here released within the water, it will tend to symbolize and cause the water to become acidic, and thus it will be then recognized that HCl is an acid because it produces hydrogen ions in the water, due to which it produces a solution which is acidic solution. Likewise, the solution which is produced over here by the dissociation of sodium and OH ions is known as the basic solution. So this is a basic concept, apart from which there are some certain things about uh, its free energy, such that when sodium OH NaOH is dissociated into water, some amount of energy is released, which is known as free energy. Same goes with HCl, when it is released, some amount of energy is produced, which is known as free energy, and that free energy causes to you know uh, form an other ionic compound which is known as salt, such that if you are having sodium hydroxide, if you are in sodium hydroxide on one hand side, and on the other hand side if we take HCl, if we are taking an acid on one hand side and a base on another hand side, when that acid and that base react together, they cause to form an ionic compound, such that here OH ions when released in water, individually we can write the equation as sodium hydroxide dissociated into sodium ion and OH ion, but when it is dissociated into water, there will be some sort of free energy released. There will be some sort of free energy released. There will be some sort of free energy released, and that free energy, let me just clearly write it here. Sodium OH NaOH released into sodium ion and OH ion. On the other side, HCl released into H ion and OH ion. Sorry, H ion and Cl ion. Such that when the dissociation occurs, there is some sort of free energy released. Free energy is released, okay. And once this free energy is released, that free energy will now tend to cause another reaction in which sodium ion plus chloride ion will combine together, and thus will form an ionic compound which is known as salt. So this would be the reaction occurring, and that reaction would be known as the neutralization reaction, which we are going to study further. Coming to the other topic, which is the limitations. Its limitations are in such a manner that Arrhenius theory is first and foremost having its limitation that it is only applicable in aqueous solution. Secondly, that some compounds are not capable of producing H or OH ions. Let's suppose if we talk about uh, ammonia is not having NH3. Ammonia, it is not having the ammonia NH3, it is not having the OH ions. So even though it is a base, so at that moment it was again a drawback or limitation. After that, when it comes to another part about the Arrhenius theory, is about is such that those compounds which neither produce H ions or OH ions, let's suppose carbon dioxide or aluminum chloride, these are compounds which do not have H neither, nor they have OH. So at that moment their acidity or basicity were also unable to be measured. So at that moment these were the drawbacks, but of course it's not a drawback because this was also helpful in the upcoming theories. When it comes to Bronsted-Lowry theory, Bronsted-Lowry theory, Bronsted-Lowry theory was presented by two scientists known as Bronsted and Lowry, such that uh, this theory indicates that those substances, there are two terminologies utilized over here: proto donor, and protophilic. Proto donor and protophilic. Those substances which are protophilic, those substances which donate proton are known as the acids, Bronsted acids, and those substances which accept protons or are proton lovers are known as protophilic or bases. So protophilic are bases, protodonor are acids. Now in this case, uh, he also provided another concept over here, which was about conjugate acid and conjugate base, such that if you're having HCl and ammonia, HCl and ammonia when reacting together, when HCl reacts with ammonia, H ions used over here, H ions used over here will, combine with, uh here HCl will donate its H ion towards ammonia, due to which it will become ammonium ion. On the other side, chloride ion would be become -1 charge over it, due to which it will become chloride. Now at that moment, ide represents negative charge, represents metal or positive charge, and ide represents negative charge or non-metal, right? So at that moment, when HCl donated its proton to NH3, it now became, uh, previously it was an acid. HCl was an acid. Now when it donated its proton to NH3, now it lost its proton, which means its ability to donate proton was finished. And when its ability to donate proton was finished, it now actually became a proton lover, which means it now had the capability to accept proton. At that moment, when it had the capability to accept proton, it was now considered as a base, and that base was formed due to the reaction of an acid. So at that moment, we can say that this was a conjugate base of the Bronsted acid HCl. So chloride was a conjugate base of the Bronsted acid HCl. Likewise, if we talk about uh, some other molecules such as ammonium, basically it is the characteristic ammonium, here NH3 had the capability to accept proton, such that it has the capability to accept proton, such that when it accepted the proton, it now had no further capability to accept proton, which means after accepting the proton, I mean, if as ammonia accepted the proton, it now lost its capability to accept proton further, due to which now it had the capability to donate proton, and it was now known as an acid, due to which it was a conjugate acid of Bronsted base. Likewise, this is known as a conjugate acid base pair and conjugate base acid pair, right? One more thing I would like to highlight over here is about uh, the relationship between conjugate acid and conjugate base. The If the base is stronger, if an acid is stronger, then its conjugate base would be weaker. If a conjugate base if an acid is weaker, then conjugate base would be stronger. Likewise, if a base is stronger, then its conjugate acid would be weaker, and if a base is weaker, then conjugate acid would be stronger. So in this case, this is the pair and relation which we are going to further derive as well. Sulfuric acid, same reaction. In that case, it gains, you know, it becomes a conjugate acid. H hydronium hydrated proton becomes conjugate acid, and bisulfate becomes conjugate base. Moreover, there are some other reactions mentioned over here as well. Apart from which, there was another condition described by Bronsted-Lowry theory, that there are certain molecules which act as acids as well as bases, which means when they react with acids, they become bases, and when they react with bases, they become acids. These substances were basically known as the amphoteric substances, amphoteric or amphiprotic molecules. Amphoteric or amphiprotic, both are the same things. These were amphoteric or amphiprotic molecules. Now let me just try to draw the periodic chart. On the periodic chart, we can first see that there are non-metals in the in the D block, in the D and F block, there are metals. And metals basically, they act as what? Metals basically have the characteristic. Now, an important point that I would like to highlight over here is that metals are have the characteristic to donate protons. Metals have the characteristic. Metals basically, let me just try to draw an structure over here. Metals are larger in size. Metals are larger in size, due to which they have less nuclear force. As a result of less nuclear force, they have electropositivity, due to which they tend to they tend to donate protons. As a result of which, as they tend to donate protons, these are basically known as the acids, whereas non-metals, according to uh, the Bronsted theory, would be considered as bases. Reason behind it is that they are electronegative. Acids, non-metals are electronegative, due to which they tend to accept electrons, accept protons as well as accept electrons, due to which they basically are known as more of the protophilic characteristics, due to which they would be considered as bases, right? But when it comes to non-metalloids or semi-metals, or metalloids, mostly, that metalloids are having both the characteristic of metals as well as non-metals, such that they can act as metal when reacting with a non-metal. They can become a, they can become an acid when reacting with a metal, and they can become a base when reacting with a non-metal. They can become a base when reacting with a metal and acid when reacting with a non-metal. So this is uh, a consequence. Moreover, there are some other parts as well, such as amphoteric molecule. Among them is, you know acetic acid. It's generally, we consider it as acid, but it's not an acid, but it is an amphoteric molecule, which means it can act as acid as well as base. Reason behind it is that it is having H ions as well as it is having OH ions. So it is having characteristic of both, acids as well as bases. Likewise, H2O is an amphoteric molecule. H2O, because it when it dissociates, it basically forms OH ions and H ions. So in this case, these are some common characteristics, apart from which the limitations of this theory are in such a manner that this theory does not provide us with the, explanation about those compounds which are not having any proton. Let's suppose aluminum chlorate once again and again. Those compounds which did not have the capability to lose or gain protons, such as carbon dioxide and aluminum chlorate, were not explained in this theory. And these were some common consequences. After that, when it comes to some common explanations here, there's a proof that uh, how, conjugate acid, conjugate of a weak base, is a strong acid here, such that if we are having this reaction, if it's a strong acid, it is a weak conjugate base, value of Ka will be larger. Now, reason behind it is the value of Ka and Kb, that why is it a strong base, why there's a inverse relationship between a conjugate base and an acid. Because there's an inverse relationship between Ka and Kb value. Reason behind it is that it has an inverse relationship between Ka and Kb value, such that if we talk about Ka and Kb value, as we have a value of Kc, which is the equilibrium constant, we are having the value of acid dissociation constant, which is known as Ka, and a base dissociation constant, which is known as Kb. Likewise, we are having value for uh, dissociation of water, ionic dissociation of water, which is known as Kw, which is known as ionization constant of water as well. We are going to discuss that up in, hopefully, right now. Now, if there's a weak acid, then there would be the less value of K, so equilibrium will be turned to the left. And if there is a more value of, if there's a strong acid, then there will be, a large value of K, due to which the equilibrium would be turned to the right. Right. So these are some common examples, apart from which, coming to the next point, we are having Ka and Kb value. Ka basically, if we talk about Ka, if we are going to, suppose to dissolve an acid, let's suppose this is an acid A with its, acidic property H, I mean the proton, and I mean the hydrogen proton, and then we are having it dissolved into water. So when it is dissolved into water, it causes to produce uh, H ions. It causes to produce hydrated proton. Hydrated proton is what? Hydrated proton is H3O, or hydroniumine, or oxyniumine. It is also known as hydroniumine, oxyniumine, or hydrated proton. Moreover, the rest of the compound which would be obtained is A negative. Now here negative sign indicates that it is an acid. Positive sign indicates it is a base, according to the Lowry theory. After that, when it comes to um, writing the equilibrium equation, it can be written as Kc is equals to product H3O concentration of H3O into concentration of acid upon HA, right? Here we are not including water because water is found in excess, so it does not have an impact on the Kc value. So when we are taking not taking water, and when we are supposed to multiply Kc with Ha, now Ha is being multiplied, divided. When we are going to send it on the other side, it would be multiplied and would now become as Kc into Ha, which is equal to H3O, right? H3O positive and A, such that this would be the equation. Now here Kc into HO, or the product of Kc and Ha, basically causes to form another product, another constant is known as Ka, which means a, a product, which means that the product, double product of the product of a constant is a constant, such that the product of two constants Kc and Ha is basically the value Ka, which is the acid dissociation constant. Acid dissociation constant. Moreover, um, when we are going to write Ka instead of Kc into Ha, then it would become as Ka is equals to H3O and A. This is the concept behind Ka, and Ka basically is equals to Kc into Ha, such that it is the product of Kc and Ha. Now, what does it actually and conceptually indicate? It conceptually indicates that Ka is basically is an acid dissociation constant, such that if the value of Ka is increased, it indicates that more of the H ions will be dissociated within the solution, uh, as a result of which, as more of the H ions will be dissociated within the solution, it will indicate that there is a stronger acid, such that if there is high value of Ka, let's suppose if there is high value of Ka, then at that moment high value of Ka basically indicates that more number of H ions are dissociated into the solution. As more number of H ions are dissociated into the solution, it indicates that there is high acidity of the solution. High acidity of the solution. Moreover, when it comes to other characteristics, if the value of Ka is decreased, then of course there would be a weak acid. Now, the value of Ka is expressed in terms of power, such that of 1 into 10 is power minus 6, 1 into 10 is power minus 14, right? So it is often inconvenient to express it in terms of power. So instead of power, we utilize another term which is known as pKa. PKa basically it is a negative logarithm of uh, Ka, negative logarithm of acid dissociation constant. Ka is the pKa, and pKa basically indicates that if there is higher value of pKa, then there is lower value of Ka, because it is a log relation. So in a log, if there is high value of Ka, there would be less value of pK, and if there would be less value of pK, there would be the stronger acid. There would be stronger acid, and the chart is given in which we have summarized how the pK and Ka value are related. Now, another concept behind it is about the Kb value. Kb is also the same. Instead of Ha, let's suppose instead of Ha we are going to utilize another compound, BOH. BOH, right? And as we are going to utilize BOH, then the compound which would be obtained in this case would be B B sorry plus OH plus H2O. Now H2O is in excess, so we are not going to write it. right? It's in excess, but conceptually it is present. Now same equation would be there, difference only will come in the values, such that Kc is equals to B, as well as there is what we call as OH, and down towards it says BOH. BOH, BOH. Now such that BOH is being divided again, it will go and multiply, due to which it will form a product which is known as Kb. And Kb is what? Kb is the base dissociation constant. Now Kb is equals to Kc into BOH. Just like Kc into Ha is Ka, and Kc into BOH is Kb. Here B represents the base part. One more thing that I would like to highlight over here is about its characteristic again. If there is high value of Kb, it indicates that high number of OH ions are there dissociated within the solution. If there is high amount of OH ions are dissociated within the solution, it indicates that high amount of OH ions dissociated within the solution indicates that there is high amount of basicity of solution, due to which we can say that higher the value of Kb, higher will be the basicity. Likewise, if there is a lower value of Kb, low basicity, again we cannot express conveniently the value of Kb, because it is in terms of power, such as 10 is power minus 10, 10 is power minus 14. So what we are going to utilize is pKb, the negative logarithm of Kb, such that negative logarithm of Kb would be this, minus log Kb, right? Minus log Kb, negative logarithm of Kb, pKb. And here that's pKb again. If there is high value of Kb, there will be less value of pKb, which means there will be stronger the base. Likewise, if there is less value of pKb, there is high value of basicity. If there is less pKb, the stronger is the base. If there is more pKb, the weaker is the base. When it comes to ionization constant of water, ionization constant of water can be expressed in such a manner that if we are supposed to ionize water, H2O, in water, H2O here, when it is ionized, it basically forms, even though H2O is a neutral compound, neutral electrolyte, neutral salt, sorry. Even though H2O is a neutral solvent, sorry, it was a mistake. So as H2O is a neutral solvent, when some of its H2O are present within the solution, so some of the H2O molecules undergo equilibrium and undergo a bit of dissociation into hydronium ions and OH ions, hydronium ions and OH ions, or oxynium ions, hydronium ions, oxynium ions, and OH ions, right? Now, when you're going to write it in terms of Kc, its Kc value will be H3O. Now, in some books, we also write it as directly H ions. The reason behind it is that H ions represents the H3O or hydrated proton, because H3O is basically a proton which is having water inside it. I mean proton which is hydrated, which means proton which is having water. So proton having water is H3O, or in other words we can also write it as H2O, H ion. So in this case we can write it both, but for our convenience we are going to write it as H3O, H3O, let's suppose. And now this is a constant. Now at you know now here the value of Kc of water, value of equilibrium constant of water is around 1.8 into 10 is power minus 16, 10 is the power minus 16, right? Whereas the amount of water which is present in terms of 1 decimeter cube, and 1 decimeter cube is equals to you know and 1 decimeter cube, how much amount of moles of water can come? According to calculation, 55 point mole of water can come in 1 decimeter cube. Sorry, 55, oops, wrong value. 55.5 mole can come in 1 decimeter cube of water. So accordingly, when we are going to multiply Kc and H2O, which means 55.5 into 1.8 into 10 s power minus 16, we'll get a constant value. Now here, water is only slightly ionized and is much bigger than H and OH, so we are going to take it as constant on the other hand side, due to which Kc into H2O, when both will multiply together, they will give us a constant value, an ionization constant of water, or the ionization product constant, which is known as Kw, and Kw has a constant value which is known as 1 into 10 s power minus 14. Now you might be wondering, as it is a Kw value, then it must have an impact of temperature, because Kw is also what? It is a it is derived from the equilibrium constant, such that it is a product of Kc and concentration of H2O. In that case, if the temperature is increased, then at that moment the value of Kw is also increased, such that at 40 centigrade, it is at the temperature which I am going writing over here, it is at 25 centigrade, or the room temperature. But at 40 centigrade, it is 3.8 into 10 s power minus 14. 40 centigrade, 3.8 into 10 s power minus 14 at 40 centigrade into 10 s power minus 14. Likewise, if we talk about uh, the rest of the value, Kw is equals to H and OH ion concentration, such that here H ion concentration here, basically H ion concentration is 1 into 10 to the power minus 7, and OH ion concentration is 1 into 10 to the power minus 7. If there is no, additional, if there is no external H or OH ion addition, or any other sort of substance is not there, then we can have the value of H and OH ion as equal to each other, due to which H OH ion being equal at equilibrium will have their values as 1 into 10 to the power minus 7 and 1 into 10 to the power minus 7 mole per decimeter cube. One more thing, that here, as you can see, uh, Kw has a characteristic that here, uh, why we are writing H and OH ions concentration equal. Reason behind it is that H and OH ions are present in equal quantity when dissociated into water. One more thing, that here, as the dissociation constant of water is in 10 s power minus 14, which means the dissociation of water is very, very, very small, and it is around that much small that out of 1 mole of water, out of 1 decimeter cube, 1 mole of water, out of 1 mole of water, only 10 s power minus 14 molecules out of 1 mole. I mean, if we are talking about 1 decimeter cube, then out of 1 decimeter cube of water, only 10 s power minus 14 molecules, out of 1 decimeter cube of water, only 10 s power minus 14 molecules are dissociated into H3O and OH. Or in other words, we can also call it, that's 50 out of 55.5 mole of water, only 10 s power minus 14 molecules are dissociated into the H3O and OH ions. Coming to the next point here is about the pH and pOH. So, discussing pH and pOH, first and foremost, what is pH? pH is generally defined as, it is basically, first and foremost, it was given by a scientist known as Lawrenson. Uh, Sorensen. So he basically gave it, and he defined the terminology pH as power of hydrogen, potential of hydrogen. And as there is, several properties of liquids, such as liquids have fluidity as the property, boiling point is the property of liquid. Likewise, property of solid is the melting point as well as geometry. But when it comes to the property of crystalline solids, property of crystalline solid is defined by property of solution. Sorry, property of solutions is defined by, basically, property of solutions is defined by the pH and pOH values. And the pH determines the number of hydrogen ion concentration present within the solution, and pOH determines the number of OH ion concentration within the solution.
If we talk about it practically, pH can be defined as the concentration of hydrogen ion, negative logarithm of concentration of hydrogen ion. pOH can be defined as negative logarithm of concentration of OH ions in the solution. Likewise, pH, moreover, when it comes to some other point of view, here we can, utilize the equation in order to define pH. pH basically it is defined by minus log of H ion concentration minus log H ion log H ion. Likewise, pOH minus log of OH ion. Now, when we are going to, study pH and pOH, we have got a relationship that pH plus pOH gives us a constant value which is of 14. Let's see how. So we know that the ionic product of water is Kw, which is given in such a manner that here there is it is in Kw is equals to 1 into 10 power minus 14. Now H3O and OH is 1 into 10 power minus 14. So when we take the logarithm can be taken in such a manner that here the logarithm taken on both sides will cause to give us the value as this, which is minus 14 log of H3O plus log of OH. Now when we are going to take minus sign common will cause to give us the answer where which would be over here in such a manner that here it will become minus log H3O plus minus log OH is equals to 14, due to which minus log H3O will be here, minus log OH will be the would be the POH negative logarithm of OH ions, and 14 is a constant. So here now the equation after replacement will become pH plus pOH is equals to 14. Now another concept I would like to highlight over here is about pKw. What is pKw? So basically we know that, coming to what is here pKw. So previously we are known about what is Kw. Kw basically it is the ionization product constant. Ionization constant of water Kw. And ionization constant of water Kw is expressed in terms of ionization product Kw. It is expressed in terms of power, such that it is expressed in terms of 1 into 10 power minus 14 mole per decimeter cube. So in this case, this is a very inconvenient value, due to which in order to convert into a convenient value, we again take a logarithm of it, and that logarithm of it can be defined as the pKw, such as pKw is equals to minus log negative logarithm of Kw as pKw. pKw. Now there is a common relationship between and Ka into Kb, such that if we take the value Ka into Kb, when we are going to multiply Ka into Kb, let's suppose, let us take the previous equations which we previously derived, right? So here, as you can see, in the previous equations, Ka was H3O into A, and Kb, Ka into Kb, Ka into Kb is equals to H3O A upon Ha into Kb. Now, what is the value of Kb? Kb over here is Kb over here is OH, right? OH into Ha upon A, because we are going to resubstitute the equation, to which the answer will be a bit changed. It will become as this, due to which when we are going to cancel it out, we'll get our answer, which is H3O into OH. Now K into Kb will be equal to H3O into OH, such that H3O into OH is equals to what? It's equals to Kw, because we know that the product of H ions and OH ion concentration would be equal to Kw, and that Kw would give us a relation which is known as Hk into Kb is equals to Kw. Now when we are going to further derive this equation, such that if we are going to take the log on both sides, Ka into Kb, log of K into Kb on both sides, then it will become as log of Ka into log of Kb is equals to log of Kw. And when we are going to take negative sign on both sides, then it will become minus log Ka is equals to minus log Kb is equals to minus log Kw, due to which it will become as pKa, due to which we know that minus log K is equals to pK, minus log Kb is equals to pKb, and minus log Kw is equals to pKw, such that when we are going to utilize that, it will become as pKa plus pKb is equals to 14, which is the equation. Again, uh, when you're going to utilize this equation, as you can see, Ka into Kb is equals to Kw, and Ka is equals to Kw upon Kb. Kw upon Kb. Now, as you can see within this equation, Kw is a constant. So, since Kw is a constant, we can remove the proportionality sign by removing the constant, and simply derive a relation between Ka and Kb such that Ka is inversely proportional to Kb. Now, this is the reason that whenever there is a strong acid, if there's a strong acid, then there will be high value of Ka, as a result of which there will be a weak conjugate base produced from that strong acid, which would be having the low value of Kb, because Ka is inversely proportional to Kb. After that, there's another concept which is known as Lewis concept, in which Lewis was a scientist who described the concept of acids and bases, such that those substances which are capable of donating an electron pair, or with those substances which have a lone pair and are capable of donating it, are known as Lewis bases, and those substances which are capable of accepting the electron pair or are lacking the electron pair are known as the Lewis acids. Now, uh, the formation of a coordinate and covalent bond occurs in case of Lewis concept, such that those substances which donate the electron pair are known as the Lewis bases, or in other words, we can say that non-metals such as nitrogen, oxygen, and fluorine, whenever they form a bond, they are nitrogen, oxygen, and fluorine. Whenever they form a bond, they basically act as bases whenever these are involved, because these possess lone pair. And whenever there are metals involved, metals basically act as Lewis acids. After that, another concept which is given over here is such that if we take cations, cations basically have positive charge, which means cations having positive charge are capable to accept electrons. As they're capable to accept electrons, these will be considered as the Lewis acids. Moreover, when it comes to uh, anions basically accept cations will be accepting electrons, due to which they would be considered as acids, and anions would be anions would be donating electrons, due to which anions would be basically considered as Lewis bases. This would be the formation. And Lewis concept can be applied on an example, a very common example: ammonia and boron trifluoride. And ammonia and boron trifluoride basically cause to form a bond through ammonia's lone pair, such that ammonia's lone pair, when reacts with boron trifluoride, it causes to give the structure uh, of Lewis concept, such that ammonia donates its electron pair, because it is having its electron pair, so it donates its electron pair, due to which it acts as a base. And boron trifluoride, since it accepts the electron pair, would be considered as an acid. Now coming to another concept over here, which is the buffer solution. Buffer basically it is a solution.
Coming to the next part, which is about the buffer solution. First, let us discuss what is a buffer. Buffer is a type of solution which causes to resist a change in pH. A solution which uh, prevents this acid or base to change its pH. To prevent a solution change its pH is known as a buffer solution, and that buffer solution basically is of two types. First includes the acidic buffer, uh, and second is the basic buffer. Such that there are two types of buffer solutions: acidic buffer solution, basic buffer solution. These are in some sort equalizer, such that they tend to resist the change in the pH of the solution, right? And in that case, if we talk about the acidic buffers have H ions concentration more than OH ions, and basic buffers has OH ion concentration more than H ions. In other words, acidic buffers have pH less than 7, and basic buffers have pH more than 7. Likewise, when it comes to the acidic buffers are produced by a mechanism. We have previously studied about the common ion effect, and here the application of common ion effect is the buffer solution. Such that here, when we are going to utilize, uh, let's suppose Um, Here, we what we are going to utilize, we are going to utilize a weak acid in order to produce. We are going to utilize a weak acid in order to produce an acidic buffer with its salt with a strong base. It's salt with a strong base. Salt with a strong base. Salt with a strong base. Weak acid plus its salt with a strong base. Likewise, when it comes to basic buffer would be the same, that there would be a weak base and its salt with a strong acid. So this is how we are going to make the buffer. Now, why we are utilizing its salt? Reason behind it is that the salt as well as the acid will be having the common ion present within them, and that common ion will basically tend to prevent a change in pH whenever there is an addition of proton, or if there is any sort of addition of you know OH ions present within them. Now when it comes to the derivation is in such a manner that here uh, you know um, if you talk about buffer example, acidic buffer example is CH3, acetic acid, and sodium acetate. CH3COOH, very common, and sodium acetate. Sodium acetate. This is a buffer solution, such that whenever we utilize weak acid, sodium, acetate, and then it's salt with a strong base NaCl, which is sodium acetate, we get the buffer solution, acidic buffer solution, which is known as CH3COOH. And important MCQ is that its pH ranges from 3.76 to 5.76, right? And when it comes to its pK value is 4.76, right? Apart from that, when it comes to some sort of derivation in order to find the pH and pOH value of buffer solutions, we have got an equation derived, which is known as the Henderson-Hasselbalch's equation. Henderson-Hasselbalch's equation, such that if we talk about the derivation, first we are having the derivation of Ka, such that this is the value of Ka is equals to proton products concentration on denominator side, and reactants on the denominator side, such that when we are going to take minus log on both sides, minus log will cause to create this type of equation, which is minus log Ka is equals to minus log an entire product concentration and reactant concentration. And then when we are going to take the log, it would be such a manner that minus log Ka is equals to minus log proton plus minus log A upon Ha. Such that by definition, what we are going to do is to take their actual values, that minus log K is equals to what, pKa, and minus log H is equals to pH, and minus log A and upon Ha would be remaining as common, right? So the equation which will be gaining over here would be pK is equals to pH minus log A upon Ha. Now in order to find the pH of the buffer solution, the log being subtracted will be added over the other side, and the final equation which would be obtained would be pH is equals to pK plus log A upon H. Likewise, if we talk about um, the value of A basically represents the weak acid. A represents the acid, and Ha represents the sorry, A represents the salt, and Ha represents the acid. A represents the salt, and Ha represents the acid, right? So here this is going to be the acid, and this is going to be the salt and acid. Now one more thing I would like to highlight over here is such that hmm, this is salt, this is acid, and whenever we are having equal concentration of salt and acid, at that moment the answer of log would be log 1, and log 1 is equals to 0, due to which when there is equal concentration of acid as well as salt, then at that moment the buffer is an ideal buffer, and that buffer has its pH equal to pKa. Moreover, when it comes to you know increase or decrease in pH, then we can accordingly find with this equation. Likewise, we are having the Henderson-Hasselbalch equation for the weak base as well, for the basic buffer. So the basic buffer equation can be found with the help of POH is equals to pKb plus log of salt. Here, instead of conjugate acid, we can write it as salt as well, right? So we can write it as salt. In our book it is salt, so we are going with salt, right? And we can also write it as conjugate acid upon the weak base which is given, such that when both are having equal concentration, then there would be an ideal buffer. Now, when it comes to some other part, we are going to discuss about salts. Coming to the next part, which is about salts. So here, salts is again a short topic in which we are going to discuss. Basically, salt is an ionic product. It is an ionic compound which is produced as a result of, a neutralization reaction between an acid and a base, such that when an acid and base react, they basically cause to release their H and OH, their acidic part H and their basic part OH, and this acidic part H and OH combine together in order to form a molecule known as H2O molecule, and rest the ionic product obtained in with regard to the you know uh, this particular salt are obtained from the acids and bases, such that the cation is obtained from the base. Cation is obtained from the base because in base we are having the anion, which is OH, and the anion in the salt is obtained from the acid, because in the salt, because in acids we are having because in acids, let's suppose we have HCl acid. HCl acid we are having the positive part as H. So positive part and negative part will go out, due to which the cation will be obtained from the base, and anion, which is the negative part chloride, will be obtained from the acid. Now there comes a reaction in which we uh, cause the reverse of neutralization, such that instead of performing neutralization, we have a process which is reverse of neutralization, which is known as hydrolysis process. Such that if you're taking a salt, let's suppose if we take NaCl, NaCl is a salt, right? So when we are going to take NaCl as a salt, and when we are going to add water in it, when we are going to perform a reaction with water, then at that moment, according then at that moment, it basically causes to produce some sort of it forms it converts back from its ionic salt form back to its acidic and basic parts, such as it forms sodium hydroxide and HCl. Now in this case, this type of reaction in which the water molecules are cleavaged, there are two terminologies: hydration and hydrolysis. Hydration is a terminology in which the water molecule is added, but it is not, their bondage is not broken between H and OH. But hydrolysis is a process in which the bond which is formed between H and OH is broken down. As a result of which, when this bond is broken down, it causes the H ions to combine with one part, the anion part of the salt, and OH part to combine with the cation part of the salt. As a result of which, it causes to form the acid and base once again, and this leads to the process which is known as hydrolysis. And this is a process in which the cleavage of the water bond takes place, as a result of which there is formation of there's back the formation of what do we call it, as the acid and base. Now whenever there is a strong acid whenever there is a strong acid and strong base, then it will cause to create a neutral salt plus H2O. Neutral salt will be created in H2O. After that, if there's a strong acid on one hand side, and on the other hand side if there is a weak base, now you might be wondering, how does this reaction occur? So this reaction occurs in such a manner that whenever there is a strong acid and strong base, the it does not occur directly. Basically, when HCl is dissolved in water, this occurs in aqueous media, by the way. So when HCl dissolves in water, it basically causes to release proton and chloride ions, right? So as it releases proton and chloride ions, HCl basically is an acid. It is a strong acid, right? It is a strong acid, and chloride is its conjugate base. Chloride is its conjugate base. Likewise, when it comes to strong base, sodium hydroxide dissociates into sodium and OH ions. Now here in this case, sodium ion, basically it is a conjugate acid. It is a conjugate acid. Now when the conjugate acid and conjugate base combine together, they cause to produce a molecule which is known as ionic compound. Conjugate acid comes from the base, and conjugate base comes from the acid, due to which, when conjugate acid and conjugate base combine together, they cause to produce a compound which is known as salt. And the properties of the salt are only showcased of the conjugate acid or base which is stronger. Let's suppose if we are having a strong conjugate acid, then at that moment, conjugate strong conjugate acids properties will be showcased, rather than weak conjugate base properties showcased, right? So at that moment, strong conjugate acids property or strong conjugate base property is showcased. Now coming to a reaction given in this diagram here, as you can see, we are having a strong acid and weak base. In strong acid and weak base, there will be presence of H ion, chloride ion, right? From the dissociation of HCl. And on the other side, we will be having a weak base, ion, ammonium ion, and OH, right? OH ion. So here in this case, ammonium would be the conjugate acid. It is, as it is obtained from a weak base, so it is a strong conjugate acid. It is a strong conjugate acid, strong conjugate acid. Likewise, when it comes to the chloride is basically a strong, it is obtained from a strong acid, so it is basically a weak conjugate base, weak conjugate base. Now when both of these will react together, the compound which would be formed would be ammonium chloride, but the properties which would be showcased would be of the strong conjugate acid because it is stronger. So ammonium will showcase its property of strong conjugate acid, as a result of which it will form ammonium chloride. Now the in a neutralize in a hydrolysis reaction particularly, or in neutralization reaction. So in neutralization reaction, uh, the if there is a strong acid and weak base, then the properties are of the acidic salt is obtained from properties of acidic salt are obtained from the base. And if there is weak acid and strong base on the alternative form, there will be the properties of base obtained from the acid, because it is a weak part and producing strong conjugate base. So in this case, this is how the properties will be obtained. These are contradict. Weak acid will provide the basic properties, and strong weak base will provide the acidic properties because of the strong conjugate acids and strong conjugate bases respectively producing a characteristic. Likewise, if there's a weak acid and weak base, if weak acid and weak base are reacting, then at that moment it depends on whether the salt will be acidic, basic, or neutral. Because it depends actually. Reason behind it is that uh, it depends on the relative value of the Ka and Kb of the weak acid and weak salt. So, in reference to the Ka and Kb value, we will be getting the actual salt, which can be neutral as well as acidic as well as basic. Now, neutral salt, of course, will have pH equal to 7, and you know will not show any color on litmus paper. Acidic salt will have pH less than 7, will show color from it will show color from red to blue, sorry, blue to red on litmus paper. Sorry, blue to red, yes. And when it comes to basic salt, basic salt will be having pH more than 7 and will dissociate OH ions. Not necessarily, but it will basically have pH more than 7, as well as it will be showcasing a litmus change from blue, from red to blue actually. So for basic salt, red to blue; for acidic salt, blue to red; and for neutral salt, there's no change in color. And these are some names of salts that you might need to remember: sodium chloride, sodium carbonate, sodium bicarbonate, sodium chloride, common salt, rock salt or table salt, kitchen salt, and sodium chloride, washing soda, sodium bicarbonate, baking soda, potassium nitrate, nitrate, and sodium nitrate, child salt, Petter, calcium carbonate, limestone, calcium sulfate, plaster of Paris. It is hydrated form. 7 H2 molecules are combined with it, and calcium phosphate bone mineral is there, which is found in our bones, as well as potassium aluminum sulfate, as well as aluminum chloride and copper sulfate in the hydrated form act as blue vitriol, and soil ammoniac, ammonium chloride. These are some important salts which we need to remember. That's about today's video. Hopefully, we'll meet again.